And we are back, and we are going to now go through our solutions to Pset 2. So for the first problem, we're asked to solve or prove that the stress tensor must be symmetric using either an energy approach or an equilibrium or static equilibrium approach. So the energy approach is a little bit kind of boring to me, but you can go. I want to go ahead and solve this using a static equilibrium approach because I think that's kind of very unique, and there's not many ways or videos or notes where it goes through it really rigorously. So in class, we've already seen one example of this, but I believe for sigma 2, 3, but now let's go ahead and let's write sigma 1, 3, because normal is in the one direction, positive 3 direction, so that's positive shear. And then let's do sigma 3, 1 as well. So normal in the 3 direction, coming out top in the positive 1 direction, so that's positive 3, 1 as well. So we know for static equilibrium, some of the forces, in this instance, some of the forces, let's do some of the forces in the 3 direction, must be equal to 0. And I can go ahead, we know that a stress is force per unit area, so we need to multiply by the cross-sectional area. So our positive sigma 1, 3, pointing in the positive 3 direction, times the area on which it's acting, which is going to be sigma 3 times sigma 2, minus basically sigma 1, 3 in the other direction, sigma 3, 2, sigma 3. So again, that's kind of a trivial, basically a trivial result, but an important result nonetheless. Equal and opposite makes sense. So that holds to be true. That looks good to us. But now let's look at the moment. So we could pick any reference point for our moment, but let's do the sum of the moment about our origin. And so we could actually go ahead and indicate right here what is going to be, or essentially where we're going to look at and where we are going to kind of sum essentially the moments in this problem. So some of the moments must be equal to 0. Let's zoom out a little bit here. Some of the forces, again, we kind of knew that implicitly. But now we can kind of move ahead and go through with basically solving this solution. So again, we're going to choose our origin just to be our kind of normal origin right here. There we go. And now we can kind of start to look at and see how we can work through this problem. So if I pick that as my origin, I need to look at how the cube will rotate when I look at, for example, sigma 3, 1. So sigma 3, 1, it's going to rotate basically counterclockwise. It's going to be positive. It works on the area sigma 1, 2, or delta 1, delta 2, and then delta 3 is my moment arm. So that's the distance from my origin. Now, the sigma 1, 3 in the opposite, that's going to rotate me clockwise, so negative. It operates on the area delta 2 times delta 3, and basically my lever arm, or my R, my angle away, is that delta 1. So with that, we can prove that sigma 3, 1 is equal to sigma 1, 3. So we already did sigma 2, 3 in the notes. Let's do sigma 1, 2. So let's erase here, draw our new cube, make sure everything is looking okay. Draw the new cube here, and let's start to write out and draw our new, basically our stresses here. So let's erase that here. So let's go ahead and finish drawing our cube. And yeah, let's redraw our stress, let's draw our new stresses. So again, we've already done 1 and 3. In the notes, we've done 2 and 3. So now we could do sigma 2, 1, that is positive direction. We can also do sigma 1, 2 in the, again, normal coming out in one direction, positive 2 directions, so those are all positive as well. So we could do some of the moments around our origin again. So if we look at sigma 2, 1, that is going to be, actually let's do, that's going to be negative because it's going to take us in our kind of our clockwise direction. And that's operating on sigma 1, 3, and then my basically distance to my origin is basically delta 2. And then my sigma 1, 2 is going in the counterclockwise direction. It's operating on delta 3, delta 2, and then the moment or the distance to the origin is that delta 1, and we get our similar expression. So we've seen this before, and this should be a little bit more essentially well known to us at this point. and how to do this problem. So I'm looking at these stress strain curves. There's ceramic, two metals, brittle polymer, ductile polymer. Identify which material is which. Ceramic, definitely that one there. Metal, these two right here, the red and the green. My brittle polymer, probably purple, because again, I'm determining that, looking at based on the slopes and the relative amount of extension. Could be gray as well. And my ductile polymer is for sure that cyan color right there. So excellent. Give approximate values on the axis for the appropriate materials that you're working with. So we know ceramics, typically they'll fail at, it varies a little bit, but 0.001 strain values. So remember, ceramics are our most brittle materials. So they aren't going to strain for too long before they fracture. And that has to do with bonding and all those other good things. Compare that to metals, actually. Ceramics, remember, they have Young's modulus about 300 gigapascals. So those are very, very stiff materials. They are elastic almost up until the point of fracture. There is obviously some plasticity involved, but it is going to be very, very minimal. So whenever you see a stress strain curve where it just looks almost completely linear before fracture, odds are maybe ceramic, depending on if it is that as well. Metals, strain at failure about 0.1. Polymers, especially elastomers, can range from 5 to 10. So you see that significant change in the order of magnitude, 3 to 4 orders of magnitude quite easily if you're just looking at the strain at failure for those materials. If you're looking on the y-axis, usually hundreds of megapascals for ultimate tensile strength is typical. For metals, Young's modulus, 100 gigapascals. For your strain at failure, or for your polymers, can range from kilopascals to 10 gigapascals, so around 1 gigapascal, pretty safe. That grade could also be a composite, maybe, who knows? And again, your y-axis is going to be in the range mostly for the metals, is on the range of hundreds of megapascals. So, excellent. We've got that. So now, which materials are strain softening? So we can look and see those materials. they increase and then they're decreasing quite a bit. So that material strain softening a little bit there, maybe, but you're not sure if that's from plasticity or other things that are happening there. Strain hardening, again, there's not super clear ones like we've seen in our other values. That could be a little bit of a strain hardening, but not many are strain hardening here. We did that intentionally to kind of look at some different ones. And then for purple, that is our perfect plastic for sure. So those are our basically materials that we are working with in terms of strain hardening, strain softening, perfect plastic as well. Excellent. So let's look at, for the blue curve, where's my yield strain? That's my yield strain. It's also basically going to be my strain at failure as well. That is my yield stress. That is my ultimate tensile stress. This is also my stress at fracture. Let's look at our Young's modulus. It's just going to be the slope there. Our UTS, we've already indicated it. Strain at failure, almost the same value there. So we could give approximate values, again, for our ceramic materials. Again, composite, so we should know many of those values already, and we've talked about those previously, and you can see those in the notes as well. So let's move on to our next problem. Identify where necking occurs for each of these materials. So it's always going to occur at our sigma UTS, so we can see that value here. We could also look at, before we move on to that one, let's look at our polymer too, in case you're looking at the different blue curve, but you can see those values, and we can see those here. Now let's move on to where necking occurs for each material. Again, that's going to look at your ultimate tensile strength here, 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 here. That's for sure where necking is definitely going to occur. Perfect plastic may, but it's not exactly sure. Maybe right at the very end for fracture there, but again, that's really where you're going to see that necking occur. Which curve is most brittle? Ceramic. Ductile, polymer. Strong. Well, if you're going by UTS, are you going by yield strength? Are you going by, what are you going by? Fracture strength. So if you're going by ultimate tensile strength, composite. Yield strength, composite. Or not, ceramic, Stress at fracture, ceramic as well. So all those ceramic materials. Most tough, I would probably say the polymer. Maybe it depends on how far we're getting out there, how small that value is, but that would be my estimation. All right, so now we need to get into some data analysis and some stress strain curves and all of this good stuff. So let's go ahead and let's look at some of our raw data file. So let's import that in. Let's look at the material that we're playing around with here. Let's open up a new Mathematica notebook and let's take a peek at this raw data. So let's paste in here. Let's paste in there. Let's go to here. And now let's get moving over here. All right. So actually, let's get back to our problem that we're looking at. And now let's do our little waiting game. But again, we want to look at this data, import it, and then essentially work with it. So we see lots of information. Let's not be overwhelmed by this. Let's just look at the first 10 rows or so. So give me the first 10 rows. Let me look at it in table form, and we can see what we're working with here. So we have some critical information. Crosshead rate, that's our strain rate. We have diameter, we have gauge length of our material, we have time, we have load that's given. Excellent. So let's go ahead and let's start to look at our initial length is going to be that gauge length, 25.4 millimeters, convert it to meters. My area, again, it's going to be pi r squared, which is 7.15 times 10 minus 3. We're going to divide that by 2 here, divide by 2, and then we're going to square that thing. Pi r squared. Excellent. And let's see, our strain rate, again, 4 millimeters per minute. So we can just do that. 4 times 10 minus 3 meters per minute. What else do we have here? All right, that's looking good so far. So we see I have a certain amount of rows that kind of give me some of this information. So let's start to grab our raw data at, let's say, about row 7. Excellent. So that's our first real data set value. So now I can start to grab my data and look at stress, strain, and basically build that engineering stress and strain definition. So we can go ahead and let's look at from 7 minus 1. All right. I could pull out all the rows on the first column. So that's my time. I'm going to divide it by 60 to make sure I'm in seconds. And this is going to be my time. And so I could define that as a variable, hide the output because I don't want to look at all that mess. And now I can start to, with my previous, actually I can copy this, and I could now grab, instead of the first column, the second column, that's my load, and I'm going to plus, give me that initial value. I want to just start everything at 0, minus, all right, there we go. They should have balanced that, but we'll just take care of that. So that's my load here. And now I could do, my stress is going to be equal to load divided by A naught. That's my engineering stress, defined there. My strain, that's just going to be simply my L naught plus that displacement, which is going to be equal to the strain rate times my time. And then I'm going to do this minus my L naught and then divide by the L naught to get my actual strain value. So let's divide by L naught, and that's my strain. So now you can just transpose strain on the x-axis, stress on the y-axis. Let's look at the list line plot, and we can get moving here. And voila, we have a very interesting stress strain curve here. It seems like it was not initially, wasn't loaded properly at the beginning. So that's going to give us a little bit of consternation. So it looks like there was some initial lack of a pull there. But we can start to measure some values. So that is my ultimate tensile stress. So that's my ultimate tensile stress. This is going to be my stress at failure, my strain at failure. Oops, it didn't look like it copied there, but I'm going to actually get my definition of yield stress and yield strain. Let's copy it right there. So that's my yield stress is about 580 megapascals. My yield strain is 0.12, and you can start to see those values. So I've got my yield strength, ultimate tensile strength, strain at failure, yield strain, Now I just need to measure my Young's modulus. So to do that, I'm going to have to start to pick out some different points here. And we could actually do a fit. So I'm just going to take some representative points here, and we are going to grab those points. Looks pretty linear to me. I messed up a little bit here. There's probably a little bit too many points, especially that initial hump there at the beginning. But I could take this data point, this data set, fit it as a linear function, and then the slope of this linear function will give me my, because I'm pulling uniaxial, so it's about 5 gigapascals. So that is already telling me maybe it's some type of brittle polymer, maybe it's some type of, maybe a composite material. I mean, we're not exactly sure. It's definitely not a metal. It's definitely not a ceramic. So I would say something like a brittle polymeric material. They can fail at, those are relatively larger strains too. Strain at failures of 0.5. So again, a 0.1 is typical of, can be typical of some metals. Other metals can be ductile, depends on if it was annealed. I just want to kind of do another plot. So you could just see how, or another fit, about 6 gigapascals, give or take. So we can kind of see those values here. So we plotted our stress strain curve, engineering stress strain curve. We've basically measured a bunch of values here. So we were able to do that quite easily, quite successfully, using Mathematica. So we've got a lot of these values. We can see now we have an estimate on what the material we're working with probably is. So maybe some type of very brittle polymer and a relatively stiff polymer as well. So let's go ahead and now see if we can solve. So we can now try to see where this intersection, actually we could solve actually for the our 0.002, actually 0.002, offset essentially yield strain, or offset yield strain measurement. So we can see here that we can find our new y-intercept in order to make sure that that intersect happens at 0. So we can basically start at that point. So we're going to offset it, keep our same slope, and then we can plot it here. And then when our basically extrapolated line intersects our actual line, then we should be, that's where we can determine essentially the yield strength. So we could plot it here, look at it. So again, this is kind of the problem with this stress strain curve. Again, it looks like they pulled, it wasn't really, completely in tension initially, because you see that kind of flat region. So, but again, this is the problem of essentially loading that stress strain curve, but also that 0.002 offset, when you could clearly kind of see linear and nonlinear regimes. So I'm not a fan of this technique, but now if you are asked to do that, and actually you could kind of see and prove that we're still doing that offset. I'm not a fan of this technique, but if you're asked to do this in industry, you can do that. So again, ideally you'd want to shift that a little bit more, but by strict definition, this is essentially, so you'd almost you get a ridiculous value for that. So your calculation hopefully is a lot better. All right, now we have to plot the true stress and the true strain values. So we have our expression. So true stress, remember. So if we remember back through the notes, we basically went through this whole conversion knowing that we need to basically conserve the volume of our system. And with that, we can derive what's that true relationship for the cross-sectional area and in terms of our engineering as well. So our true stress will be engineering stress times 1 plus engineering strain. For a true strain, we did a similar relationship. And we found it's the natural log. So remember, not log base 10, natural log of 1, I believe. Actually, let's get brackets. 1 plus engineering strain. I believe so. Yes. Let's type it out. And true stress, true strain. And we could transpose that now. And then let's see how it looks like on our graph. Again, true strain on the x, true stress on the y. And then we can take a look at that and plot it. Again, I'm going to do this line plot because I'm looking at data. I'm going to get rid of all that other stuff. Let's plot it. Plot style. I'm going to make this red. And again, I'm just not in my plot range. So all I'm going to do is simply just paste it in here. We'll use the other plot range. You see now that actually we're kind of off a little bit in terms of the actual strain values, in terms of overcounting. But the key thing we see here is that our red curve is always above the blue curve. Makes sense. Good. You see kind of that weird breakdown at the end. So first, let's actually I'm going to get it a little bit. Let's change our plot range. Let's go. Let me get out of this transpose. Let me go over here. Plot range. Okay, plot style, plot range. And I'm going to go, let's just say, again, for my x-axis 0 to 0.5 or 0.6. And then I'm going to go from 0 to, say, 10 times 10 to the 9 for stresses. And let's just do 1. Nope. How about, let's do 2 and 1.5. That looks a little bit better. So this is looking good so far. But one of the things that we should understand or appreciate is that, again, this expression only holds up until my ultimate tensile strength. So I want to find the position, where does my ultimate tensile strength exist? So I can only plot this from the first component or the first value up until 271. So that's where this expression is actually true. Once you start to neck, that expression breaks down, so we can no longer use that. Excellent. So write the stress tensor for the example below. So we can see here that I have my sigma 3,3, that's compressive, negative. Got that. Sigma 2,2 is positive. Sigma 1,1 maybe, but we'll come back to that. I think that's... So let's look it over here. So my normal's in the 3 direction, and it's pointing in the negative 2 direction, so that's minus sigma 2,3. I could also look at that value in the, again, I have a normal in the 3 direction, and it's pointing in the negative 1 direction, as we can see here. So negative 3,2, negative 2,3. So again, 3 direction, negative 1 direction, so negative 1,3, negative 1,3, and that sigma 1,1 should be 0. So that's just a little... I was misreading my own diagram, which, again, happens from time to time. I can make a mistake. So 0, 0, 0, and we're good to go. So how about drawing the RVE for our stress tensor that we see there? Well, we can see that in the 2,2 we are compressive. So I can just draw that like so. Compressive, we can nail that one out. Let's look at our next one that we can kind of eliminate. So again, normal in the 1 direction, pointing in the negative 2 direction. So we got that one. What else? So we can now go, again, normal in the 1 direction, pointing in the positive 3 direction. Fantastic. And then finally, normal in the 2 direction, pointing in the negative 3 direction. That is my minus sigma 2,3. We got it. So now we can move on to this problem. I'm going to zoom out a little bit, and then I'm going to go ahead and quit my kernel so that we can start to work in this problem. This is a very, very important problem, one that will be most likely some version of it on your exam. So let's make sure that we work on this one and do this problem exceptionally well. So we have a new mystery cubic material, and it is a simple cubic material, and we're given this potential description here. So we have UR is equal to A times 1 minus exponent B times R minus C, and then we need to have this whole thing squared. We know that force, interatomic force, is equal to minus derivative of UR with respect to R. And we're given that our R naught, our equilibrium distance, is 2.86 times 10 to the minus 10. Oops, put that equal here. And we also know this value of force F max is equal to 10 times minus 10 piconewtons. Now, this is a very important distinction here. This force maximum value we are going to have to basically change this to a different sign, but we'll come back to that in a second. And pico is to the 12, so excuse me for that mistake right there. And then we know that our y is going to be 69 times 10 to the 9th. Excellent. So we need to determine the fitting parameters, units. We already know the units. A has to be in joules, B needs to be in inverse meters, and C has to be in meters as well. And then we need to find maximum stress, maximum strain. Number of nearest neighbors, it's simple cubic, so we know it's 6. So we know our Z, number of nearest neighbors, is going to be equal to 6. And now we can start working on this problem. So what can we start to solve? Well, we know our equilibrium distance, so let's go ahead and try to solve U of R. We know that we need to solve when this is equal to 0. Our energy is minimized. We've reached our equilibrium distance. Let's solve for the real value. So our equilibrium distance is going to be equal to our C parameter. So C is equal to R naught. So 1's down. Excellent. We're also given our Young's modulus expression. So I'm going to say Young EQ is going to be equal to Y, which is going to be equal to Z over R naught times the derivative of our UR second. And then I'm going to evaluate this where R goes to R naught. We also know the value of our maximum force. But one of the questions is, what's the distance where that force is maximized? So I want to find derivative of force with respect to R, and I want to be able to solve, basically solve when does this equal 0, what value of R, and it has to be a real value as well. So that's going to be that value there. So we need to be able to, and then basically I know that my F max equation is going to be when my force is maximized. That is going to be when I basically plug in force slash dot R goes to this value. So I have this equation here. So right now I have one equation with 2 unknowns, one equation here with 2 unknowns as well. So we could actually go ahead and plug in, actually we see here, yeah, there's no R's here. So we could ostensibly solve right now. So I could solve F max equation. I could do Young equation. Oops, and I could solve it for, let's see, solve it for A and B. Uh-oh, it's not allowing us to work like that. Why is that? Do you see anything wrong in here? F max equation, F max, we have a value here. We're plugging in R in terms of these other variables. Why are we not allowed to solve this one? Does anyone see what's happening here? One of the things we have to think about also is, again, this is our force max, our value of force, which we're given in this problem, but this is not, that's the force that the material experiences. But this is the force in between my particles. So I need to flip the sign of this F max. So I could do that. Still have my Young equation. Still have my F max equation. I could solve, or I could try to solve for this. But it looks like we're going to have, and let's zoom this out here. We need to also solve for what is this value here. So we plug this into our equation, but we also need to solve for basically when does this equal 0. So we want to solve one more equation, which is our R at F, or our R when our force is maximized is going to be equal to the derivative of the force set it equal to 0. And then that's going to be our equation. So here we have an R in this equation as well. So we need to solve for A, B, and this particular value of R. So RF max. And then now we can solve this problem. So again, we needed to solve for first, what is this, R value effectively. So we have 3 equations with 3 unknowns here. So I have my R, my RF max. I want to call it this right here. This is my RF max. Actually, I'm going to call it my F max R. Bad notation. A, we have that value. B, we have this value. Excellent. What's our maximum stress? Well, we know that for a cubic material, our A naught is going to be equal to basically basically our R naught value. Our R naught value is effectively 2R, so A naught is going to be equal to R naught. So keep that in mind that this is equal to 2R, so our metallic radius would be half of that, 1.43. So we've got this. So I've got that. Number of nearest neighbors. We need to figure out the material, but maximum stress will just be F max. This divided by F max and divided by A naught squared. And again, it's the force that's that opposite direction. You can look at the magnitude. So this would be the maximum stress exerted on our material. Our strain will just be, and again, you know the force here, we had to kind of plug that in there. You could also just take the negative here, so it's kind of inconsequential. So you could do the negative just to look at the magnitude, because we know it's going to be in tension. Our F max R, our maximum strain is going to be our F max minus R naught. That's our initial distance divided by R naught. And that's our strain, positive, looking good. That's our maximum strain. Now we're asked, what material is this? So if I look at my periodic table, we need to look for a metallic radius that is 1.43. So I'm going to search 1.43. So let's see, where's my match? Aluminum, but aluminum is what? FCC. So that's not going to work because we're simple cubic. We're also assuming it's a metal. May not be metal. Where else do we find that 1.43? Where is it? Tantalum. But again, that is not, first off, that's the covalent radii, not the metallic radii. So this is not, it's an alien material, maybe an alloy, maybe something else. So now we can go on to number 6. Thermodynamic variables in the Gibbs free energy equation were significant, which were neglected. So then we need to look at the potentials, describe the stiffness, compliance, and all these other good things. So we need to look back and think about our expression that we, actually, how did we derive and how do we get that expression where the Young's modulus is equal to second derivative of our potential? So we did our, thermodynamic analysis, and we found that our stress was equal to 1 over the volume times the change in our internal energy over the change in our strain minus TDS over VD epsilon, And we said that, well, as we pull material, the entropy of a metal or polymer that's less than TG is not going to change significantly, and that's how we're able to kind of find those values. So looking at the potentials, how can we describe the stiffness of each curve? Well, I know for that first cyan curve, that has a stiffer Young's modulus than the red, and then the red has a larger one than the orange, because I could just look at the curvature, the second derivative, the shape of that potential. So that is for sure the case. Which has the largest equilibrium distance? Definitely the orange. So I could just see that, again, that minimum energy on that curve for sure. If these were all the same material but at different temperatures, rank the temperatures? Well, again, looking at your equilibrium distance and seeing that, I could definitely see that. And then the shape of the potential kind of dropping or widening. T3 is greater than T2 is greater than T1. So that is Pset 2 in the books. Get started on Pset 3, and I'll see you the next time. Thanks. Bye.